Okay, welcome everybody to today's lecture. We're going to talk about applications of double integrals to problems from physics, and I'm sure you see the same things come up in your engineering classes. So the first application is density and mass. Okay, so in your Calculus 2 class, I'm sure you were exposed or should have been exposed to how to compute moments and the center of massive points or collections of points. Now we want to do the center of mass and the moments of inertia and the second moments of a very thin plate, or as the book refers to it, a lamina. So it doesn't have to be any particular shape. It can have an unusual shape, but what we do need it to have is the property that it's so wide and long compared to the thickness that you can essentially assume it's two-dimensional. Okay, so we're going to say that the lamina occupies a region capital D of the XY plane, and its density can vary from point to point. So the density is a function, rho, of its position, X and Y. And the density has to be continuous. It can't jump from being 0 at one point to being non-zero at to being completely positive at another point. And no cracks, okay? In other words. So the density, what does a density mean? Mass density. It means the mass per unit area. So that you can think of the density as being the limit as the delta A goes to 0 of the delta M over delta A. So delta M is the mass of a little rectangular area, and delta A is the area of that little blue shaded area, so a little generic rectangle in the region. And the density at a particular point in that rectangle would be obtained by taking smaller and smaller rectangles about the point. Okay. It's the mass per unit area. Okay. All right, so how do you find the total mass of the lamina? So you place the lamina in R2, you stick it in the plane, and now you grid up the plane, just like we did when we were developing double integrals. So that gives you a bunch of rectangles. He's using slightly different notation here than I did, because you grid it up one way in the X direction, a different way in the Y direction. He's keeping track of both of those on each subscript, a little bit overkill, but okay. So you grid up the area into sub-rectangles. You pick one generic rectangle. We're going to call that Rij. We're going to focus on that for a moment. Pick your favorite point in that rectangle. It can be anywhere as long as it's in that rectangle, even on the border of that rectangle. Okay, so that favorite point is going to be Xij star, Yij star. Okay. Then the mass of the lamina that occupies this little rectangle is approximately equal to the density at this point times the area of that rectangle. So that's all he's saying here. It's the density times the area. That's about the mass of that ijth rectangle. And now we do it for every rectangle. That means we sum over I and j, and that gives us an approximation to the mass of the total lamina. Sorry, too fast. Now you put in more and more sub-rectangles. In fact, you start putting in so many that you let the number in the I direction and the number in the j direction go to infinity. Okay, so what happens when you do that? Well, you get a Riemann sum, and that's a Riemann sum for what? Well, if you stare at this for a minute, you see that's the double integral over d of rho of x and y dA. Okay, so there's the mass. The mass is the limit of this Riemann sum. In other words, the mass is the double integral over the region of the mass density dA. That's really not a news flash. If I had asked you to guess, you would have probably guessed that. Okay. You can also talk about other types of density and treat them in exactly the same way. For example, you could do it. Suppose you knew a charge density. which we'll call sigma at every point in a region. Then you could compute the total charge in the region by just integrating the charge density over that region. So the moral of the story is if you have something like a charge density, a mass density, something like that, so that it is a mass or a charge per unit area, you get the total by just integrating. Okay. So let's look at an example, a simple example, kind of cooked up example. So suppose you have a charge distributed over over the triangular region that's shown here. Okay, and for some reason, we know that the charge density at a point xy is just x times y. Okay, and it's measured in coulombs per square meter. And we want to know what's the total charge on this triangular region. Well, we're going to have to take the double integral of x times y over this region. And how do you write that? Well, it depends on what you want to integrate first, but the way the picture is doing it, with vertical lines, you're integrating with respect to y first. So this line is y is 1 minus x. The top line is y equals 1. The borderline for the left-hand limit is x equals 0, and the borderline for the right-hand limit is x equals 1. So our total charge is the integral over d of the charge density dA. So that means we go from 1 minus x to x. Those were our limits on y in that triangle. Then x went from 0 to 1. This was given to us as the charge density, and we integrated first with respect to y, then with respect to x. Okay, so if you integrate y with respect to y, you get y squared over 2, evaluated from the upper limit to the lower limit. So if you put that x and the 2 together, you get an x over 2. You have 1 minus x quantity squared. So that is 1. So inside this parentheses is 1 minus 2x minus x squared. I'm sorry, plus x squared, but you're subtracting it. So you have a 1/2 when you, and that gives me a 2x squared minus x cubed when you, let's see, when you go back, let's for a second. Because you had the x times everything. So the ones cancel, but then you had a minus 2x with a minus sign out in front. That gives you a plus 2x. So that becomes a 2x squared. And then you had a plus x squared, but this makes it a minus x squared and times the x. So that gives you the minus x cubed. Okay. All right. So now when we have to integrate this with respect to x. So that gives you 2x cubed over 3 minus x to the 4th over 4. And you evaluate from 1 to 0 and you do all the arithmetic. You get 5 over 24. And the charge was measured in coulombs. So the answer, the total charge comes in coulombs. Okay. Excuse me. So it's just a question of doing the double integral. Okay, so that's really all there is to mass. It's really not a lot. Okay, so now let's go to moments and center of mass. Okay, so now we know how to find the center of mass of a lamina. I mean, we know how to find the total mass of a lamina. Now we want to find the center of mass. What is the center of mass? It is the point where if you put that lamina and rested it on a fulcrum exactly at the center of mass, then the lamina would balance. Okay. So suppose we're again going to say we have our region D and it has density. This lamina has density rho given by rho of x and y. And now we, if you remember from calculus 2, that the moment of a particle about an axis is its mass times the directed distance from the axis. So that's just when you have one particle. But now we have a lamina. So how do we find the moment of the lamina about an axis? Okay. Well, we're going to take our lamina, we're going to grid it up, we're going to find a typical rectangle, the ijth rectangle. And then we pick our favorite point in it, that xi star, xij star, yij star. And now the mass in that rectangle is approximately given by the density at that point times the area. So we approximate the moment about the x-axis by measuring the directed distance from the point xij star, yij star to the x-axis. Well, that's given by the what? That's given by the y-coordinate of xij star, yij star. So here's the mass, or the approximation to the mass on that rectangle, times the directed distance from that point to the x-axis. Okay. And once you have that, now what do? We do the same exact thing that we've done before. You sum it over all the rectangles. That's what here. Then you put in more and more rectangles. So in other words, let m and n go to infinity. And then you stare at that for a minute and you realize, whoa, that's a Riemann sum. It's a Riemann sum for the double integral of y times rho of x and y dA. So there's the formula for the moment about the x-axis. And that's really all you need to remember here, that this is the formula for the moment about the x-axis is given by the double integral of y times rho times the density dA. And students often confuse that, but remember, when you're doing a moment about an axis, you want to use the directed distance to that axis, which comes from the opposite coordinate. So the moment about the x-axis has a y times the rho in the formula. And same sort of argument would give you the moment about the y-axis, which would be the double integral of the directed distance to the y-axis, which is given by the x-coordinate, times the density dA. Okay. And what's the center of mass? Well, it's the point when the mass times x bar gives you the moment about the y-axis, and the mass times the y bar gives you a moment about the x-axis, just like it did in calculus 2. And as I mentioned, the physical significance is that the lamina behaves as if its entire mass was concentrated at that one point, the center of mass. So here are here's basically a summary of all the formulas and the depiction of how if you put a fulcrum at the center of mass, then the lamina would balance. Okay. So the coordinates of the center of mass are given by the moment of inertia about the y-axis divided by m. That gives you the x coordinate. And here's a reminder of what the moment about the y-axis formula is. It's a double integral of x times the density dA. And the mass, that m, is just the double integral of the density over the region. And similarly, the y-coordinate of the center of mass is m sub x divided by little m. And the moment of inertia about the x-axis is the double integral of y times the density dA. Okay, so these three formulas, including the expressions for capital MX and capital MY, summarizes all you need to remember when you go to work problems on this section, on this material. We're going to go on and do a couple more things. Okay. So what about a moment of inertia? So the moment of inertia, which is also called the second moment, and you saw this in the probability lecture too. The moment of inertia about the axis is defined to be mr squared, where r is the distance from the particle to the axis, and little m, of course, is the mass. Okay, so now you want to extend it to a lamina. We're in 2 dimensions. So the lamina has the density rho, and so how do we extend this idea of what was true for a particle to a lamina? Well, as you might have guessed by now, you take that lamina, divide it up into rectangles, and then use the fact that the moment of inertia about each little rectangle, when you're using a particle as a point in that rectangle, can be obtained by taking a Riemann sum. So let's see how that goes. So when you take the moment of inertia about the x-axis, you have to use the distance to the x-axis, which is given by the y-coordinate of the point that you've chosen in the rectangle. And you want the radial distance. So that, let me go back one thing. Let me remind you, it was mr squared, not just m times r. That's the second moment, okay? So that is the directed distance squared. And here's your approximation to m. It's rho times delta A. So this summand right here is the approximation to the moment of inertia from the point xi, from the ijth rectangle. We do that over all the rectangles to get an approximation. Then we put in more and more rectangles. And then you notice this is a Riemann sum. So the moment of inertia about the x-axis is the double integral of y squared rho dA. Hence the name second moment, y squared. So basically the first moment is the moment about the x-axis we got before. The second moment is the moment of inertia, okay? Okay. And similarly, if you do the moment of inertia about the y-axis, you have to use the directed distance to the y-axis, so it involves x squared times rho dA. Okay. The other quantity that is sometimes of use in physics is the moment of inertia about the origin, or the polar moment of inertia. So there you have to measure the directed distance from the point that you chose in your subrectangle to the origin and square it. But that's just the radial distance. So that is xij star squared plus yij star squared. The distance would be square rooted, but we're squaring it, so we end up with this. And then you multiply by the mass. That gives you the approximation on the rectangle. Do you see we're doing the same thing over and over? Add up all the rectangles and put in more and more rectangles. And what do you end up with? You end up with a Riemann sum for the double integral over the region of x squared plus y squared times the density dA. Okay. And then notice you never have to calculate all three of those moments, because the moment about the origin, the polar moment of inertia, is the sum of the moment about the x-axis and the moment about the y-axis, those two moments of inertia. Okay. All right, so let's do an example, a very easy example, but that has some interesting observations associated with it. So let's find the moments of inertia about the x-axis, y-axis, and the polar moment of inertia of a homogeneous disk. That means constant density with density rho. Notice it's a constant. The disk is centered at the origin and has radius A. Okay, so once you have a disk that's a circle, you should be suspicious immediately that you're going to want to use polar coordinates for your double integrals. And how do you write the boundary of the disk? Well, it's x squared plus y squared equals a squared. That's not a secret. And so in polar coordinates, that is, you let r go between 0 and a, and let theta go between 0 and 2 pi to describe the whole disk. Okay, so let's calculate the polar moment of inertia. So that's a double integral over d of x squared plus y squared times the density, which in this case is constant. It's just rho dA. So let's convert to polar coordinates. So r goes from 0 to a, theta goes from 0 to 2 pi. The density is constant, so I move it out in front. This x squared plus y squared gets replaced by r squared. Okay. And then the dA in polar coordinates is r dr d theta. Okay, so I have an r, whoops, let me go back and point this out. So that gives me an r cubed dr. And then notice there's no other theta dependence in here. So you just have the integral from 0 to 2 pi of d theta times the integral from 0 to a of r cubed dr. So that's what you have up here. When you integrate the d theta, you get 2 pi. When you integrate r cubed, you get r to the 4th over 4 from a to 0. So all total, that gives you a pi rho a to the fourth divided by 2. Okay, so that's the polar moment of inertia for this problem. And then they got clever about this because we know we don't have to compute all 3, but we know even more because it's a constant density. So that's a key in this little observation right here. So the density's the same in every direction at every point in the circle. And the circle itself is perfectly symmetric, right? The circle is the ultimate symmetric shape. So we know that I sub x has to equal I sub y because everything is symmetric, and the moment of inertia about the x-axis plus the moment of inertia about the y-axis has to both add up to this. Okay, so that means that 2xi, if you like, equals I0, and 2y I sub y is I0. In other words, each one of those moments of inertia is equal to half of the polar moment of inertia. So that is pi rho a to the fourth over 4. And I emphasize that if our density had not been constant, this last line and this observation would be false, even though it's a circle. Okay. Okay. So now let's like a little observation about this particularly very special setup. So because the density is constant, the mass would just be the density times the area. So the density was rho, the area of the circle is pi times the a squared. So the moment of inertia of the disk about the origin, which was pi rho a to the fourth over 2, we can write that as the 1/2 out in front. Let's write the rho pi a squared, and let's break up the a squared. So notice that the rho pi a squared, that's the mass. So you could write the polar moment of inertia is 1/2 the mass times a squared. So what does that say? That says for a homogeneous wheel, if you like, the moment of inertia increases like the first power of the mass, but the square of the radius. But if you increase either the mass or the radius, then you increase the moment of inertia. Okay. And okay. Yeah, so I'm not going to go on to radius of gyration. So the moment of to summarize, the formulas that you need to remember from this section are, let me go back and start over. Okay. Whoop. So the formulas we need from this section are that the mass, little m, of a region is the double integral of the density over the region. If you have a charge density, you can get the total charge in the region by integrating that over the region. You need to know moments of inertia about the axes. So mx is the double integral of y times the density over the region. The moment of inertia about the y-axis, I'm sorry, the moment about the y-axis, not the moment of inertia, is the double integral of x times the density. And the center of mass is given by the x coordinate of the center of mass is the moment about the y-axis divided by the total mass. The y coordinate of the center of mass is the moment about the x-axis divided by the mass. And then the moments of inertia formulas. That the moment of inertia about the x-axis is y squared, so it's a second moment times the density. The moment of inertia about the y-axis is x squared. And the polar moment is x squared plus y squared times rho. In other words, it's the sum of the second moments about the x and y axes. Okay, so just lots of formulas. They give you enough information to be able to write down those formulas, and then it becomes a question of just doing the double integrals. Okay. All right, so now you have all the information you need to work the problems for 15.4. that will be due in the following week. And any questions you have, you can ask in class on Monday. Okay, hope that was helpful, and